What if I told you that everything, every star, every planet, every speck of dust floating in the sunlight outside your window was once compressed into a space smaller than a single atom? That every piece of matter in the universe, from the mountains to the oceans to the air in your lungs, traces its origins back to an explosion of energy so unimaginably powerful it gave birth to reality itself. This is the story of the Big Bang, the moment our universe roared into existence, and it's a story so strange, so utterly mind-bending, that it challenges everything we think we know about time, space, and even the nature of existence. Picture this: 13.8 billion years ago, there was no space, no time, no galaxies spinning in the void, just an unfathomable concentration of energy, hotter and denser than anything we could ever recreate. And then, in a fraction of a second, it burst outward, expanding faster than the speed of light, setting the stage for everything that would ever be. But here's the wildest part: we're not just talking about an explosion in space. The Big Bang created space, it created time, and when we peer back into the depths of the cosmos, we're actually seeing echoes of that primordial event, clues etched into the fabric of reality itself. So how did this cosmic seed, this tiny, infinitely hot speck, transform into the vast universe we see today? What forces sculpted the first atoms, the first stars, the first galaxies, and perhaps the most haunting question of all, what, if anything, came before the Big Bang? Over the course of this journey, we'll unravel these mysteries together, from the dizzying concept of cosmic inflation to the moment light finally broke free in the newborn universe. This isn't just a story about science, it's the story of us, of how we came to be, and how every time we look up at the night sky, we're staring directly into our own past. So buckle up, reality is about to get a lot stranger. The Big Bang Theory isn't just some wild guess, it's the most well-supported explanation we have for how our universe began. But here's the twist: it wasn't an explosion in space. Instead, think of it as space itself stretching, swelling from something unimaginably small to the vast cosmos we know today. Picture a balloon inflating, with galaxies as dots on its surface, drifting farther apart as it expands. That's closer to what happened. One of the biggest clues supporting this idea is something called the cosmic microwave background. Imagine turning an old TV to static, that faint hiss and snow. About 1% of that crackle is actually leftover radiation from the Big Bang itself, a faint glow from when the universe was just 380,000 years old. It's like finding the heat signature of creation, still lingering after nearly 14 billion years. Then there's Edwin Hubble's groundbreaking discovery in the 1920s. By observing distant galaxies, he noticed something mind-blowing. The farther away a galaxy was, the faster it seemed to be moving away from us. This wasn't galaxies racing through space, it was space itself stretching, carrying them along like raisins in rising bread dough. Together, these pieces of evidence paint a picture of a universe that's not just expanding but had a definite, fiery beginning. But here's what makes the Big Bang Theory so revolutionary: it doesn't just explain where things are now. It tells us that time itself has a starting point. There was no before, because the Big Bang created time along with space and matter. Trying to imagine what came before it is like asking what's north of the North Pole. The rules we know break down at that unimaginable moment, where all the energy and matter in existence was packed into a space 1 trillion times smaller than a grain of sand. And from that single, searing instant, everything we see, everything we are, began to unfold. Long before telescopes and particle accelerators, cultures across the world wrestled with the same profound question: how did everything begin? Ancient Hindu texts describe a golden cosmic egg, floating in emptiness before cracking open to release the universe. Norse myths speak of a fiery abyss where worlds formed from the bones of a giant. These stories feel eerily familiar today because they echo a fundamental truth humanity somehow sensed: our existence sprang from something unimaginably small and potent. For centuries, Western science clung to a very different idea that the universe was eternal and unchanging. Even Einstein, when he formulated his theory of relativity, initially tweaked his equations to avoid implying the cosmos had a beginning. It wasn't until the mid-20th century that the steady-state model, championed by astronomers like Fred Hoyle, proposed matter was continuously created to fill the gaps as the universe expanded. No explosive birth, no dramatic origin, just an endless, gentle unfolding. But the evidence kept piling up, that faint microwave static, the redshift of galaxies racing away. These weren't just quirks. They were screams from the past, insisting the universe had a fiery infancy. The cosmic egg wasn't just myth, it was prophecy. Modern cosmology tells us that all matter, all energy, was once compressed into a singularity so dense, the laws of physics as we know them didn't apply. Yet here's the beautiful irony: those ancient storytellers gazing at the stars weren't so far off. They lacked telescopes but not imagination, and sometimes imagination brushes against truth in ways we're only now beginning to understand. What's astonishing isn't just how wrong we used to be, but how fragments of the answer were hiding in plain sight all along. The steady-state model, elegant as it was, couldn't explain the scars of creation we now see etched across the sky. Meanwhile, myths carried whispers of cosmic beginnings that science would spend millennia catching up to. Both roads, one paved with equations, the other with poetry, led us to the same staggering realization. Everything we know, everything we are, began when the universe decided to wake up. Einstein's equations of general relativity were like a cosmic prophecy, one he didn't fully believe at first. When he applied his groundbreaking math to the universe as a whole in 1917, the results were shocking. The numbers insisted space itself couldn't stay still. It had to be either stretching or collapsing like a living, breathing thing. But this flew in the face of what everyone, including Einstein, assumed about the cosmos, that it was eternal, unchanging, static. So convinced was he that the universe must stand still, he tweaked his own equations by adding something called the cosmological constant, a fudge factor, to keep everything perfectly balanced, frozen in place. Years later, he'd call this move his greatest blunder, because while Einstein was busy propping up his vision of a motionless cosmos, other scientists were staring at his original, unaltered equations and seeing something revolutionary. A Russian physicist named Alexander Friedman took those same numbers in the 1920s and showed they demanded a universe in motion, either swelling outward or crunching inward, but never static. Then came Georges Lemaitre, a Belgian priest and physicist who took Friedman's work even further. He proposed something radical. If the universe was expanding now, then rewinding time meant everything must have once been packed into a single, unimaginably dense point. He called it the primeval atom, what we now know as the Big Bang. The irony is delicious. Einstein, the iconoclast who shattered Newton's clockwork universe, became the conservative clinging to old ideas. Meanwhile, Lemaitre, blending theology with cutting-edge physics, saw what Einstein couldn't: that the universe had a birthday. It wasn't until Edwin Hubble's observations in 1929, galaxies racing away from us in all directions, that Einstein finally conceded. The evidence was too overwhelming. Space wasn't just stretching, it was carrying the echoes of an ancient explosion Einstein's own math had predicted. What makes this more than just a historical footnote is how it reveals science at its most human. Even geniuses resist their own discoveries when they clash with deeply held beliefs. Einstein's cosmological constant wasn't just a mathematical term, it was a safety net, a way to keep the universe familiar. Yet in a twist worthy of poetry, that same blunder would later stage a comeback. Modern dark energy research suggests the cosmological constant might describe a real force pushing the universe apart. So perhaps Einstein's mistake wasn't adding it, but ever doubting his equations in the first place. The lesson here isn't just about expansion or constants. It's about how often the truth hides in plain sight, waiting for someone brave enough to take the numbers at face value. Lemaitre did that, armed with nothing but faith in the math, and in doing so, he glimpsed the fiery dawn of everything. Edwin Hubble didn't set out to rewrite cosmic history, he was simply measuring stars. But in 1929, while peering through the 100-inch Hooker telescope at Mount Wilson Observatory, he stumbled onto something that would shatter humanity's understanding of the universe forever. By studying distant galaxies, Hubble noticed something peculiar about the light they emitted. The farther away a galaxy was, the more its light shifted toward the red end of the spectrum. This wasn't just a curiosity, it was a cosmic fingerprint. That redshift meant galaxies were racing away from us and the most distant ones were fleeing the fastest. What Hubble had uncovered was the universe's most breathtaking secret. Space itself was stretching, carrying galaxies along with it like leaves caught in a rushing river. This wasn't just an observation, it was the smoking gun for the Big Bang. If everything was moving apart now, then rewinding time meant there had to be a moment when all of it, every galaxy, every atom, was crushed together in a single searing point. Hubble's discovery turned a controversial idea into the cornerstone of modern cosmology. The key to quantifying this expansion lies in something called the Hubble constant. Imagine it as the universe's speedometer, a number that tells us how fast space is stretching at any given distance. If a galaxy is 1 million light-years away, the Hubble constant tells us exactly how much faster it's receding compared to a galaxy half that distance. But here's where it gets even more fascinating. By measuring this constant, we can actually calculate the age of the universe. It's like finding a cosmic clock hidden in the motion of galaxies. Current estimates put the Hubble constant at about 70 kilometers per second per megaparsec, meaning for every 3.26 million light-years you look out into space, galaxies appear to rush away 70 kilometers per second faster. Yet this elegant idea hides layers of complexity. The Hubble constant isn't just a number, it's a battleground for modern astronomy. Different methods of measuring it keep yielding slightly different results, sparking what scientists call the Hubble tension. Some measurements, like those from the Planck satellite studying the cosmic microwave background, suggest a slower expansion rate. Others, like observations of pulsating stars called Cepheid variables, point to a faster one. This discrepancy isn't just a minor glitch, it could hint at unseen forces or even new physics lurking in the fabric of reality. Hubble's breakthrough did more than prove the universe was expanding. It gave us a way to trace its history back to that first unimaginable moment. Every galaxy racing away from us carries a piece of the story, a clue written in light. And just like Hubble, we're still peering through the telescope, still unraveling the mysteries his discovery set into motion. The universe isn't just expanding, it's inviting us to follow the trail of light back to its birth. At the very beginning, time zero, the universe wasn't just small. It wasn't just hot, it was everything crammed into nothing. A singularity where all the energy, all the matter, every law of physics we rely on today, collapsed into a point so unimaginably dense it defies language. Infinite temperature, infinite density, a state where space and time ceased to have any meaning we'd recognize. This wasn't a place you could point to because there was no where for it to exist. No before to precede it, just a searing, unfathomable knot of pure potential. Think of it this way, take every star in every galaxy, every black hole, every particle of dust between them, and crush it all down until it's 1 billion times smaller than a grain of sand. Then keep going, past atoms, past quarks, past anything with a name. That's the singularity, a realm where gravity becomes so overpowering, it twists the fabric of reality itself. Our equations of general relativity, which beautifully describe the universe from microseconds after the Bang onward, snap like twigs when pushed back to this moment. They spit out infinities, a sure sign we're missing something fundamental. This is where quantum gravity must step in. Einstein's relativity governs the vast cosmos, while quantum mechanics rules the tiny world of particles. But at the singularity, these two titans collide, and they don't play nice. To truly understand the birth of the universe, we need a theory that merges them, something like string theory or loop quantum gravity. These ideas suggest the singularity might not have been a true infinity, but a quantum foam of fluctuating space-time where the usual rules took a breather. What's wild is that the singularity isn't just a relic of the past. Black holes contain their own singularities, hidden behind event horizons. Study one, and you're peering into a mirror of the universe's first moment. Both are places where matter becomes pure geometry, where the weight of existence crumples reality into a mathematical abstraction. The difference, the Big Bang's singularity wasn't hidden, it was everything. And from that impossible seed, somehow, the universe blossomed. So when we say the universe began as a singularity, we're really admitting how much we don't know. It's a placeholder, a way of saying, here be dragons. Our physics hits a wall, and beyond it lies uncharted territory, where time might loop, dimensions twist, or entirely new laws emerge. The singularity isn't the end of the story. It's the door to a deeper mystery, one we're still learning how to unlock. Every telescope, every particle collider, every equation scribbled on a chalkboard is an attempt to push that door open just a little wider. The Planck Epoch is where physics as we know it throws up its hands and surrenders. For the first 10 to the power of -43 seconds after creation, a span so brief, even calling it a moment feels absurdly long. The universe existed in a state so extreme our current laws can't touch it. This was the realm of quantum gravity, where the energy density was so immense, gravity itself behaved like the other fundamental forces, blending seamlessly with them in a single, unified interaction. To grasp how alien this environment was, consider the Planck temperature, a staggering 1.4 times 10 to the power of 32 degrees Kelvin. That so hot temperature ceases to have any practical meaning. Matter as we know it couldn't exist. Even protons and neutrons, the building blocks of atoms, were impossible here. Instead, the universe was a seething ocean of pure energy, where particles flickered in and out of existence so rapidly, they barely had time to register their own presence. At these energies, the four fundamental forces we take for granted today, gravity, electromagnetism, and the strong and weak nuclear forces, were indistinguishable. They weren't separate phenomena but different facets of a single, unified superforce. It's like watching water separate into ice and steam as it cools. What we now perceive as distinct forces were once one, locked in perfect symmetry. Only as the universe expanded and cooled did they freeze out into the separate interactions that govern reality today. But here's the catch: we don't have equations that can fully describe this epoch. General relativity, our best theory of gravity, breaks down at these scales. Quantum mechanics, which governs the ultra-small, can't account for the crushing gravitational effects. Bridging this gap requires a theory of quantum gravity, something physicists have chased for decades, with contenders like string theory and loop quantum gravity still in play. The Planck Epoch is like a cosmic crime scene where the usual clues have evaporated, leaving us to reconstruct the events from the faintest of traces. One tantalizing possibility is that space-time itself wasn't smooth and continuous in this era, but foamy and fluctuating, a quantum froth where tiny bubbles of space and time popped in and out of existence. Imagine trying to navigate a stormy sea where the very concept of here and now dissolves into chaos. That's the Planck Epoch, not just the beginning of time, but a place where time might not have behaved like time at all. What makes this more than just theoretical gymnastics is how it shapes everything that followed. The conditions of these first instants set the stage for the universe's entire evolution. The way forces split apart, the way space-time stabilized, these were the first strokes on a cosmic canvas that would eventually give rise to galaxies, stars, and us. The Planck Epoch might be an enigma, but it's an enigma written into the fabric of reality itself, waiting for us to decode its secrets. If the early universe had a growth spurt, it would make even the most dramatic teenage growth spurts look glacial. In less than a trillionth of a trillionth of a trillionth of a second, space itself stretched by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. To put that into perspective, if you scaled a single atom up by that same amount, it would suddenly dwarf the entire observable universe. This mind-boggling expansion, known as cosmic inflation, was proposed by physicist Alan Guth in 1980 to solve some of the Big Bang's biggest mysteries. One of those puzzles is called the horizon problem. Look at the cosmic microwave background, the afterglow of the Big Bang, and you'll notice something strange. No matter which direction you point your telescope, the temperature is nearly identical, varying by less than 1 part in 100,000. But here's the catch. In a universe expanding at a leisurely pace, there hasn't been enough time since the Big Bang for distant regions to exchange heat and even out their temperatures. It's like walking into a room where 2 cups of coffee on opposite sides have somehow cooled to the exact same temperature without ever being near each other. Inflation fixes this by proposing that every patch of the early universe was once crammed together in an infinitesimal space, already in thermal equilibrium before being dramatically stretched apart. Another head-scratcher inflation solves is the universe's startling flatness. Measurements show space-time on cosmic scales is almost perfectly flat, meaning parallel lines stay parallel indefinitely, not curving inward like a sphere or outward like a saddle. Without inflation, achieving this level of flatness would require the universe to have been fine-tuned to an absurdly precise degree at its birth, like balancing a pencil on its tip for billions of years. But rapid expansion acts like a cosmic iron, smoothing out any wrinkles or curves until the universe appears flat, no matter its initial shape. Guth's breakthrough wasn't just about solving problems, it introduced a radical new actor onto the cosmic stage, the inflaton field. Picture this as an invisible energy field that permeated the early universe, driving inflation like an engine running at full throttle. As the field decayed, its energy transformed into the hot soup of particles we recognize from the Big Bang. Think of it like a stretched rubber band snapping, except instead of making a loud noise, it released the raw ingredients for stars, galaxies, and eventually us. What's truly wild is that inflation suggests our universe might be just one bubble in a frothy multiverse. If inflation can happen once, why not in countless other regions, each birthing their own cosmos with different physical laws? It's a humbling thought that what we call everything might be a tiny speck in a much vaster, stranger reality. Inflation's fingerprints are all over the universe, from the pattern of galaxies to the faint whispers of gravitational waves that might one day be detected. It's a theory so powerful, so elegant, it reshaped our understanding of cosmic beginnings. And yet, like all great scientific ideas, it leaves us with even more questions than answers, like why inflation started or exactly how it ended. For now, it stands as our best explanation for how a speck smaller than an atom could blossom into the vast, intricate cosmos we call home. As the furious expansion of inflation tapered off, the universe settled into a new phase, one so extreme, it makes the core of the sun feel like a winter breeze. This was the era of quark-gluon plasma, a seething ocean where temperatures soared above 2 trillion degrees Celsius. At these energies, even protons and neutrons couldn't hold themselves together. Instead, their building blocks, quarks and gluons, roamed freely, crashing into one another like ingredients in a cosmic blender set to maximum speed. Quarks, the fundamental particles that usually huddle in groups of 3 to form protons and neutrons, were now unshackled. Gluons, the sticky particles that bind quarks together through the strong nuclear force, flitted between them like hyperactive messengers. The entire universe resembled a dense, opaque soup where matter and energy were indistinguishable. Light couldn't travel far before being absorbed and re-emitted, making the cosmos as murky as a storm cloud. Then, around 1/1,000,000th of a second after the Big Bang, things began to change. As the universe expanded, it cooled just enough for quarks to start feeling the pull of the strong force again. Like strangers at a party suddenly recognizing their friends, quarks began pairing up in 2s and 3s. Mesons formed from quark-antiquark duos, while triplets of quarks created the first protons and neutrons, the building blocks of atomic nuclei. But this particle assembly line had a dramatic twist. For every quark that survived, there was nearly an identical antiquark. When matter and antimatter meet, they annihilate in a flash of pure energy. Most of these particle pairs vanished in blinding bursts, leaving behind only photons. Yet somehow, against all odds, a tiny surplus of matter remained, roughly 1 extra quark for every billion annihilations. This minuscule excess is the reason anything exists at all. Had matter and antimatter been perfectly balanced, their mutual destruction would have left the universe empty, a void without stars, planets, or people. Instead, that 1 in a billion imbalance became the raw material for everything we see today. Every atom in your body, every star in the sky, owes its existence to this cosmic accounting error written into the laws of physics. What caused this asymmetry remains one of the greatest unsolved mysteries in science. Theories like CP violation suggest subtle differences in how matter and antimatter behave, but the observed effects are too small to explain the scale of our universe's survival. Some physicists speculate undiscovered particles or forces tip the scales, while others explore exotic ideas like parallel antimatter universes. The Quark Epoch wasn't just a chaotic free-for-all, it was a delicate balancing act where the slightest tilt determined the fate of reality. As temperatures continued to drop, protons and neutrons emerged from the fray, setting the stage for the next dramatic chapter, the formation of the first atomic nuclei. But without those early survivors, the quarks that outlasted annihilation, none of what came next would have been possible. The universe, it turns out, was built on a razor's edge. 380,000 years after the Big Bang, the universe finally caught its breath. Until this point, space had been a roiling sea of charged particles, protons, electrons, and nuclei, all crashing about in a frenzied dance, bouncing photons back and forth like a cosmic game of pinball. Light couldn't travel more than a hair's width without being scattered, making the universe as opaque as a storm cloud. But then, something monumental happened. The temperature dropped just enough for electrons to slow down and be captured by atomic nuclei, forming the very first neutral hydrogen and helium atoms. This moment, called recombination, marked the universe's first true clarity. With electrons no longer running wild, photons could finally travel unimpeded, a phenomenon we now see as the cosmic microwave background, or CMB. Imagine a fog suddenly lifting after eons of blindness, revealing the structure of reality for the first time. That faint glow filling our radio telescopes today. It's the afterimage of that exact instant, stretched over billions of years into microwaves by the expansion of space. The CMB isn't just a relic, it's a time capsule. Its temperature fluctuations, tiny variations of just 1 part in 100,000, reveal the seeds of all cosmic structure, those slightly denser patches. They're the gravitational blueprints for galaxies, clusters, and the vast cosmic web we see today. Without them, matter would have spread too evenly, and stars might never have ignited. The universe would have remained a featureless void. What's astonishing is how perfectly this snapshot has been preserved. The CMB's temperature, now just 2.7 degrees above absolute zero, matches predictions with uncanny precision. It's like finding a fossil from the dawn of time, perfectly intact, whispering secrets about the universe's infancy. When astronomers map its subtle ripples, they're effectively reading the universe's birth certificate encoded in microwaves. Yet the CMB holds even deeper mysteries. Its near-perfect uniformity hints at inflation's staggering expansion, while its slight irregularities beg questions about dark matter's invisible hand. Some patterns in the data might even suggest our universe collided with another in its infancy, a phantom imprint of other realities brushing against our own. Recombination didn't just create atoms, it set the stage for light to sculpt the cosmos. Those liberated photons, racing unimpeded for the first time, began weaving the tapestry of everything we see. And every time we point a telescope at the CMB, we're not just observing history, we're witnessing the moment the universe stepped out of the shadows and into the light. With the glow of recombination fading, the universe plunged into an era of profound darkness, a cosmic midnight lasting hundreds of millions of years. No stars pierced the void. No galaxies swirled in the black, just an endless sea of neutral hydrogen gas stretching across the expanding cosmos like a thick, unbroken fog. This was the cosmic dark ages, a time when space was so devoid of light sources it would have been utterly invisible to human eyes. Yet beneath this stillness, invisible forces were at work. Gravity, the universe's quiet architect, began weaving the first delicate threads of structure. Tiny density fluctuations left over from the Big Bang, those faint wrinkles in the cosmic microwave background, acted like seeds for creation. Wherever a slightly denser patch of gas existed, gravity pulled more hydrogen toward it. Over eons, these pockets grew, drawing in surrounding matter with increasing urgency. Picture mist gathering into droplets on a cold window. Except here, the droplets were proto-galaxies, and the window was the fabric of space itself. The physics of this era were deceptively simple. Without stars, the only sources of heat were residual warmth from the Big Bang and the occasional release of energy when hydrogen atoms collided and formed molecular hydrogen. These molecules, though rare, became crucial. They allowed gas clouds to cool and condense further, accelerating gravity's work. Still, progress was achingly slow. The universe stretched 100 times larger before the first stars finally ignited. Then, around 200 million years after the Big Bang, the darkness cracked. In the densest regions of those primordial gas clouds, hydrogen became so compressed that atoms began fusing together. The first stars, known as population Roman III stars, blazed to life with a fury unmatched by anything in the modern cosmos. Unlike today's stars, which contain heavier elements, these pioneers were pure hydrogen and helium, and their size defied belief. Some may have been hundreds of times more massive than our Sun, burning hot and fast before exploding as supernova within a few million years. Those cataclysmic deaths marked the end of the Dark Ages and the dawn of a new epoch. The explosions seeded space with heavier elements, carbon, oxygen, iron, polluting the pristine hydrogen gas and setting the stage for the diverse stars and planets we know today. Meanwhile, ultraviolet radiation from the first stars began stripping electrons from surrounding hydrogen atoms, a process called reionization that gradually made the universe transparent to light once more. What's remarkable is how fragile this transition was. Had gravity been slightly weaker or molecular hydrogen less efficient at cooling gas, the Dark Ages might have stretched far longer or never ended at all. Instead, those first stars became cosmic lighthouses, their light piercing the fog and illuminating the path to everything that followed. Their birth wasn't just a turning point, it was the moment the universe learned how to shine. Imagine stars so colossal they dwarf our Sun like a candle next to a bonfire. These weren't just the first stars, they were cosmic titans, blazing with a brilliance that tore through the darkness of the early universe. Known as population Roman III stars, they formed from the purest ingredients available: hydrogen and helium left over from the Big Bang, uncontaminated by heavier elements. Without metals to help them cool and collapse efficiently, these stellar behemoths grew to staggering sizes, some possibly reaching several hundred solar masses. Their sheer scale meant they burned at temperatures we can barely comprehend, turning their cores into furnaces hot enough to forge the very first heavy elements in existence. The life cycle of these primordial giants was as brief as it was spectacular. While our sun will shine for billions of years, population Roman 3 stars lived fast and died young, some lasting only a few million years before meeting spectacular ends. When their cores finally exhausted their hydrogen fuel, they didn't just fade away. They detonated as supernovae so violent they outshone entire galaxies, scattering newly forged elements like cosmic shrapnel across the void. Carbon, oxygen, even traces of iron, these weren't just byproducts. They were the raw materials for everything that followed: rocky planets, organic molecules, and eventually life itself. What makes these ancient stars truly extraordinary is how they transformed the universe's chemistry. Before them, the periodic table was practically empty, just hydrogen, helium, and trace amounts of lithium. But in their cores, nuclear fusion worked like an alchemist's crucible, smashing atoms together to create heavier elements for the first time. When these stars exploded, they didn't just vanish. They became galactic gardeners, planting the seeds for future generations of stars, planets, and even the molecules that would one day form our bodies. Yet their legacy goes beyond mere stardust. The ultraviolet light pouring from these first stars began ionizing the surrounding hydrogen gas, stripping electrons from atoms in a process called reionization. This monumental shift turned the universe from an opaque fog back into the transparent expanse we know today, allowing light to travel freely across cosmic distances. Without this pivotal transition, the cosmos would have remained shrouded in darkness, and we'd have no way to peer back through time with our telescopes. Remarkably, we've never directly observed a population Roman 3 star. Their light faded eons ago, stretched by cosmic expansion into infrared wavelengths too faint for current telescopes to detect. But their fingerprints are everywhere, etched into the composition of later stars, encoded in the distant gas clouds they enriched, and whispered in the patterns of the cosmic microwave background. Future observatories like the James Webb Space Telescope may finally catch glimpses of these elusive pioneers, spotting their faint glow in the furthest reaches of space and time. Their story is a reminder of how deeply interconnected everything truly is. The calcium in your bones, the oxygen in your lungs, the iron in your blood, all of it was forged in the hearts of stars that died billions of years before Earth even existed. We are quite literally stardust given consciousness, a way for the universe to look back on itself and marvel at how far it's come. The deaths of those first stars weren't an ending, they were the beginning of everything we know. The universe didn't just make stars, it wove them into grand designs. After the first generations of stars blazed to life, something even more extraordinary began to unfold. An invisible architect, dark matter, started sculpting the cosmos, drawing gas and stars into swirling cities of light we call galaxies. This wasn't random. It was gravity's meticulous work, guided by mysterious dark matter's unseen hand. Picture dark matter as the universe's hidden framework. Unlike normal matter, it doesn't emit, absorb, or reflect light, yet its gravitational pull is relentless. In the early universe, dark matter formed vast, tangled webs with dense knots where galaxies would later bloom. As these invisible structures grew, ordinary matter, hydrogen and helium gas, flowed into their gravitational wells like water filling valleys. Gas clouds collided, compressed, and ignited new stars, lighting up the dark matter's blueprint. The first galaxies were born not from chaos, but from an intricate cosmic choreography. Our own Milky Way is a product of this process. Around 13 billion years ago, a small clump of dark matter began gathering gas, forming a proto-galaxy no bigger than a globular cluster. Over eons, it grew hungrier, merging with smaller galaxies and devouring their stars. Each collision left scars, streams of stars still visible today, arcing across our galaxy's halo like celestial brushstrokes. The Milky Way didn't form in isolation. It's a mosaic of stolen stars, a testament to the violent beauty of galactic evolution, but the real drama unfolded on larger scales. Galaxies didn't just form, they clumped together, drawn into clusters and superclusters by dark matter's gravity. These clusters became nodes in the cosmic web, connected by filaments of gas and dark matter stretching across billions of light years. When galaxies collided, their stars rarely crashed. Space is too vast, but their gas clouds slammed together, triggering furious bursts of star formation. Some mergers birthed monstrous elliptical galaxies, while others, like the future collision between the Milky Way and Andromeda, will reshape both into something entirely new. What's astonishing is how much of this structure traces back to quantum fluctuations in the universe's first moments, tiny ripples magnified by inflation into the seeds of galaxies. The cosmic web isn't random. It's a frozen echo of the Big Bang's fingerprint, written in dark matter and illuminated by stars. And as we map deeper into space, we're not just seeing galaxies, we're reading the universe's diary, page by page, from its first whispered words to the epic it's still writing today. Just when cosmologists thought they had the universe figured out, it threw them a curveball, one that would rewrite the cosmic rulebook. In 1998, two independent teams studying distant supernova made a jaw-dropping discovery. The universe wasn't just expanding, it was accelerating. It was like tossing a ball in the air, only to watch it shoot faster into the sky instead of falling back down. This wasn't just unexpected, it defied everything we thought we knew about gravity's grip on the cosmos. The culprit, a mysterious force dubbed dark energy, making up a staggering 68% of the universe's energy budget. Dark energy isn't just another cosmic ingredient. It's the anti-gravity glue holding the future of the universe in its hands. Unlike dark matter, which pulls galaxies together with its gravitational tug, dark energy does the opposite. It pushes space itself apart. Picture it as an invisible spring woven into the fabric of reality, growing stronger as the universe expands. When the cosmos was younger and smaller, gravity-dominated galaxies clumped together, stars ignited, and structures formed. But around 5 billion years ago, dark energy took the wheel, stretching space faster and faster until one day, distant galaxies will vanish beyond an unreachable horizon. The implications are as profound as they are unsettling. If dark energy's push continues unchecked, the universe faces a big freeze, a slow, cold fade into isolation. Galaxies beyond our local group will eventually accelerate away so fast their light will never reach us. Millions of years from now, civilizations born in those distant islands of stars will look up and see nothing but darkness, their skies emptied of everything beyond their own galaxy. It's a lonely endgame where the universe doesn't just expand, it disintegrates. But here's where it gets stranger. We still don't know what dark energy actually is. The leading theory suggests it might be the cosmological constant, an energy intrinsic to empty space itself, first proposed by Einstein and later discarded as a way to balance his equations. Quantum physics predicts vacuum energy should exist, but its calculated strength is off by a factor of 10 to the power of 120. That's not just a rounding error, it's the worst prediction in the history of science. Alternative ideas, like a dynamic quintessence field that changes over time, remain on the table, but for now, dark energy is a placeholder for our ignorance. What makes this mystery even more tantalizing is how it ties into the universe's earliest moments. Inflation, that ridiculous exponential expansion in the first sliver of a second, might have been driven by a similar repulsive force. Could dark energy be inflation's dimmer cousin, a weaker version of the same physics? Or is it something entirely new, a cosmic wild card we've yet to comprehend? Every telescope and sky survey now hunts for clues, from the Large Synoptic Survey telescope mapping billions of galaxies to ESA's Euclid mission studying the universe's accelerating architecture. Dark energy didn't just change our understanding of the universe, it flipped the script on cosmic destiny. For centuries, we assumed gravity would eventually slow the expansion, perhaps even reverse it in a big crunch. Now we know the cosmos has other plans. The universe isn't just drifting apart, it's racing toward an invisible finish line we're only beginning to glimpse. And whether that future is cold solitude or something stranger, it's a reminder that the cosmos still guards its deepest secrets fiercely. The cosmic microwave background isn't just radiation, it's a time machine. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a strange hiss in their antenna at Bell Labs in New Jersey. No matter where they pointed it, this persistent noise remained like static from a broken TV. They scrubbed the equipment clean of pigeon droppings, checked every connection, yet the anomaly wouldn't vanish. What they'd stumbled upon wasn't a technical glitch, it was the afterglow of creation itself, cooled over 13 billion years to just 2.7 degrees above absolute zero. This accidental discovery earned them a Nobel Prize and gave humanity its first direct glimpse of the universe's infancy. Those faint microwaves paint a revolutionary picture. Imagine looking at a newborn's first photograph, but instead of chubby cheeks, you're seeing the universe at just 380,000 years old, a glowing plasma of hydrogen and helium, hot as the surface of a star. The CMB captures the exact moment this primordial soup cooled enough to let light travel freely, freezing a snapshot of cosmic structure in its earliest form. What's astonishing is how uniform it appears. The temperature varies by less than 1 part in 100,000 across the entire sky, a testament to inflation's stretching effect smoothing out wrinkles in space-time. But those tiny fluctuations are where the magic hides. Slightly denser regions appear as cooler spots in the CMB, while thinner areas are warmer. These imperfections, smaller than 1/100th of a degree, might seem insignificant until you realize they're the blueprints for everything. Gravity amplified these minute differences over eons, pulling matter toward denser regions until galaxies and galaxy clusters emerged. Without those microscopic ripples, the cosmos would have remained featureless. We owe our existence to quantum fluctuations smaller than a proton, magnified by inflation into the seeds of cosmic structure. Modern telescopes like Planck have mapped these variations with stunning precision, revealing patterns that answer profound questions. The distribution of hot and cold spots confirms the universe is geometrically flat to within 0.4%, a direct prediction of inflation. Their angular sizes reveal the exact mix of ordinary matter, and dark energy. Some patterns even hint at gravitational waves from inflation's first moments, though that evidence remains hotly debated. Perhaps most haunting is what the CMB doesn't show. Its perfect blackbody spectrum lacks any distortions, telling us nothing violent disturbed the universe's expansion until the first stars ignited 200 million years later. It's a silent witness to the cosmos' most uneventful yet crucial phase. When we observe the CMB, we're not just studying ancient light. We're decoding the universe's genetic code, written in microwaves across the sky, waiting 13.8 billion years for intelligent life to read it. While the Big Bang theory stands as cosmology's crowning achievement, it's not the only idea scientists have explored. Some theories propose the universe didn't begin with a bang at all, but with a bounce. The bouncing universe model suggests our cosmos emerged from the collapse of a previous universe, like a phoenix reborn from its own ashes. Imagine space contracting until quantum effects halt the collapse, triggering a rebound into expansion. No singularity, no true beginning, just an endless cycle of universes breathing in and out across eternity. It's an elegant solution to the singularity problem, but here's the catch. We've found no observational evidence of a prior collapse imprinted on our universe. Equally intriguing is the cyclic model, where parallel universes collide in higher dimensional space, sparking new big bangs like cymbals clashing in an infinite symphony. Each collision resets the cosmic clock, with dark energy playing the role of conductor, pushing universes apart after each collision to set the stage for the next cycle. Yet this theory struggles to explain the precise uniformity we see in the cosmic microwave background. Without fine-tuning, such collisions would leave chaotic fingerprints rather than the eerily smooth patterns we observe. Then there's steady-state cosmology's radical proposition. The universe has always existed, with new matter continuously appearing to fill the gaps as space expands. No explosive origin, no dramatic finale, just an eternal, unchanging cosmos where the overall density remains constant. While philosophically appealing, this idea was dealt a fatal blow by the discovery of quasars and the cosmic microwave background, which clearly show the universe evolving over time. Even the distribution of galaxies tells a story of change, not stability. What keeps the Big Bang theory dominant isn't stubbornness, it's predictive power. It correctly foretold the CMB's existence and temperature decades before detection. It explains the abundance of light elements like hydrogen and helium with stunning precision. Most rivals must contort themselves to match these successes, bolting on ad hoc fixes that lack the Big Bang's elegant consistency. That doesn't mean alternative theories are worthless. They push scientists to test the boundaries of accepted wisdom, ensuring the Big Bang earns its stripes rather than resting on dogma. Some mysteries, like dark energy's true nature or what preceded inflation, leave room for speculation. Perhaps future discoveries will reveal our Big Bang was just one event in a grander multiverse. But until another theory can match both the evidence and the explanatory breadth of this reigning champion, the story of our universe's birth remains for now a tale that begins with a bang. The universe's grand tapestry, those glittering galaxies, vast cosmic voids, and sprawling filaments of matter, all trace their origins back to tremors smaller than a single atom. In the first trillionth of a second after the Big Bang, space wasn't just expanding. It was a seething quantum foam where particles and energy flickered in and out of existence like static on an untuned radio. These quantum fluctuations, normally vanishing in the blink of an eye, were caught in inflation's relentless stretch, magnified from subatomic shivers to cosmic-scale ripples that would shape everything. Imagine blowing up a balloon with tiny wrinkles on its surface. As it inflates, those minuscule creases grow into vast valleys and ridges. Inflation did the same to space-time, stretching quantum jitters into density variations, regions where matter was ever so slightly more or less packed together. These became the gravitational seeds for all structure. The slightly denser patches pulled in more gas, growing into galaxies, while the emptier regions stretched into the voids between them. What began as quantum chaos became the universe's blueprint. We see this blueprint frozen in time within the cosmic microwave background. Those faint temperature variations, some spots a hair warmer, others cooler, aren't random noise. They're direct snapshots of those primordial density fluctuations, imprinted when the universe was just 380,000 years old, the cooler spots. They mark denser regions where photons had to climb out of deeper gravitational wells, losing energy along the way. The warmer patches, thinner zones where light escaped more easily. It's as if the universe left us a fingerprint, its ridge patterns encoding the quantum storms of its birth. What's staggering is the scale of this transformation. Fluctuations that started 100 billion times smaller than a proton now span hundreds of millions of light years. The largest galaxy clusters we see today, like the Coma supercluster, grew from quantum ripples no more dramatic than a single extra atom in a room full of air. Yet without these microscopic imbalances, gravity would have had nothing to work with, no variations to amplify, no structures to build. The universe would have remained a featureless soup, silent and starless. This quantum-to-cosmic connection isn't just theoretical. Precision measurements of the CMB's fluctuation patterns match predictions from quantum physics and inflation with uncanny accuracy. The statistical distribution of hot and cold spots, how many large versus small variations exist, aligns perfectly with what you'd expect if inflation stretched quantum noise. It's like finding a symphony's sheet music and realizing every note was composed by the random vibrations of atoms. Yet mysteries linger. Why did inflation amplify fluctuations to exactly the right amplitude for galaxies to form? Too strong and matter would have collapsed into black holes. Too weak and gravity couldn't assemble stars. Some theorists suggest deeper principles at work, perhaps a universe finely tuned for complexity, or a multiverse where countless other cosmic experiments play out with different rules. For now, we know this. Every time we gaze at the night sky, we're seeing quantum mechanics written across the heavens, a reminder that the smallest and largest scales of reality are woven together by the threads of inflation's explosive dawn. The universe should have cancelled itself out. According to everything we know about particle physics, the Big Bang should have created equal amounts of matter and antimatter, particles that are identical in mass but opposite in charge. When matter and antimatter meet, they annihilate in a flash of pure energy. So why does anything exist at all? The fact that we're here pondering this question means something tipped the scales in matter's favor, just one extra particle for every billion annihilations. This tiny excess is the reason galaxies, planets, and people exist today. But what caused this cosmic imbalance remains one of the most profound puzzles in science. In the mid-1960s, Russian physicist Andrei Sakharov outlined 3 conditions that had to be met for matter to dominate over antimatter. First, the universe needed processes that violated baryon number conservation, essentially, reactions that could produce more matter than antimatter. Second, there had to be violations of both charge symmetry, C symmetry, and charge parity symmetry, CP symmetry, meaning particles and their antiparticles couldn't behave exactly the same way. Third, these processes had to occur out of thermal equilibrium during a time when the universe wasn't uniform enough for matter and antimatter to re-annihilate completely. We've actually observed CP violation in action. In 1964, experiments with neutral kaons, exotic particles that flip between matter and antimatter states, showed they decay slightly differently than their antiparticles. Later, the LHCb experiment at CERN found similar asymmetries in B mesons. But here's the catch: the observed CP violation is far too weak to account for the universe's survival. It's like finding a single drop of water when you expected a tidal wave. This discrepancy has physicists hunting for new sources of asymmetry. Some theories propose undiscovered particles that tip the scales, like heavy neutrinos or hypothetical particles predicted by supersymmetry. Others suggest the imbalance might trace back to the very first moments after the Big Bang, when extreme energies could have triggered phase transitions, cosmic hiccups in space-time that temporarily separated matter and antimatter. Experiments like those at CERN Large Hadron Collider are probing these ideas by smashing particles together at near light speeds, recreating conditions not seen since the universe's first microseconds. Meanwhile, deep underground labs are searching for rare decays in protons or neutrons that could reveal new physics beyond the standard model. Even the cosmic microwave background might hold clues. Subtle patterns in its polarization could hint at primordial processes that favored matter. The stakes couldn't be higher. Solve this puzzle, and we might finally understand why the universe didn't vanish in a burst of mutual destruction, fail, and we're left with a haunting gap in our knowledge, an existential riddle written into the fabric of reality itself. Every atom in your body is a survivor of that ancient imbalance, a fingerprint of a mystery that's still unfolding. The same physics that stretched our universe from a quantum speck to cosmic vastness might have done far more. It could have birthed countless other universes, each with its own unique laws. This is the multiverse hypothesis, a dazzling consequence of inflation theory that pushes the boundaries of reality itself. Picture inflation not as a one-time event, but as an endless process, a cosmic froth where new universes constantly bubble into existence, each pinching off from the others like soap suds in an infinite bath. At the heart of this idea lies eternal inflation. While inflation ended in our observable universe about 13.8 billion years ago, quantum fluctuations suggest it never stopped everywhere. In some regions, inflation slows and allows matter to condense into stars and galaxies. That's our universe's story. But in others, inflation keeps raging exponentially, creating ever-expanding space where new universes nucleate at random. Over infinite time, this process would spawn a fractal multiverse, where every possible variation of physical constants plays out somewhere. Some universes might have stronger gravity, rendering stars impossible. Others could lack electromagnetism, never forming atoms. Ours, with its Goldilocks perfect balance, is just one page in an infinite library of realities. The implications are staggering. If true, the multiverse could explain why our universe seems so finely tuned for life. With infinite tries, even astronomically unlikely combinations become inevitable. But it's also deeply controversial. How do you test a theory where every possible outcome exists somewhere? Some scientists argue it veers into philosophy, while others point to potential fingerprints in the cosmic microwave background. Certain anomalies in the CMB's temperature patterns, like mysterious cold spots, could hint at collisions with neighboring universes in the multiverse's foam. Even wilder are the string theory landscapes, where each universe crystallizes with different extra dimensions folded in unique ways. Imagine a cosmic kaleidoscope where every twist locks physics into new configurations. In some, dark energy dominates so fiercely that space rips apart instantly. In others, gravity crushes everything into black holes before galaxies form. We might live in a rare oasis where the numbers lined up just right, not because of design but pure statistical luck. Critics counter that without observable proof, the multiverse remains speculative. But proponents fire back. So were black holes and atoms once. Whether cosmic accident or inevitable structure, the multiverse hypothesis forces us to confront a humbling truth. Everything we call the universe might just be our local neighborhood in a reality far stranger than we ever dreamed. The story of our universe unfolds like an epic saga, each chapter marked by dramatic shifts in temperature, energy, and structure. It all begins in the Planck Epoch, the first 10 to the power of -43 seconds, where temperatures soared beyond 10 to the power of 32 degrees Kelvin. At these unimaginable energies, the four fundamental forces of nature were fused into a single, unified superforce. Space-time itself was a seething quantum foam, fluctuating wildly with no recognizable particles or even a clear distinction between matter and energy. This was the universe at its most alien, existing in a state where our current laws of physics simply break down. By the time the universe reached 10 to the power of -36 seconds, it entered the grand unification epoch. Gravity had already split from the other forces, but electromagnetism and the nuclear forces remained bound together. Temperatures cooled slightly, though still trillions of times hotter than the core of the sun, allowing the first particles to flicker in and out of existence. Then came inflation, an exponential expansion that stretched the cosmos from subatomic size to something vastly larger in less than a blink. This explosive growth smoothed out irregularities, setting the stage for the universe we see today, while simultaneously magnifying quantum fluctuations into the seeds of galaxies. At around 10 to the power of -12 seconds, the electroweak epoch began. The universe had cooled enough for the strong nuclear force to separate from electromagnetism and the weak nuclear force. For the first time, particles like quarks and gluons could roam freely, though temperatures were still so extreme that protons and neutrons couldn't yet form. This quark-gluon plasma was a seething, opaque sea where light couldn't travel far before being scattered. By the 1-second mark, the cosmos had cooled to a mere 10 billion degrees, just cool enough for quarks to bind together into protons and neutrons. But this was no peaceful transition. A great annihilation occurred with matter and antimatter colliding in bursts of energy. Only a tiny imbalance, about one extra quark for every billion annihilations, allowed matter to dominate. Had the scales tipped the other way, the universe would have faded into nothingness. Fast forward to 380,000 years, and the universe finally became transparent. Recombination allowed electrons to join protons, forming neutral hydrogen and helium atoms. Light, previously trapped in the dense plasma, broke free, creating the cosmic microwave background that still lingers today. The universe had taken its first true breath, setting the stage for gravity to sculpt the first stars. From there, the cosmic dark ages gave way to the dawn of light. 200 million years after the Big Bang, population Roman 3 stars ignited, their colossal forms fusing hydrogen into heavier elements. These pioneers lived fast and died violently, seeding the cosmos with the raw materials for planets and life. Over billions of years, galaxies clumped together, drawn by dark matter's invisible hand, while dark energy began its slow but relentless push to accelerate the expansion. Today, 13.8 billion years later, we're the beneficiaries of this intricate timeline, each epoch a crucial step in building a universe capable of wonder, complexity, and curiosity. Every photon we detect, every galaxy we map, is a messenger from these formative eras, whispering the story of how everything came to be. One of the biggest misconceptions about the Big Bang is the idea that it was an explosion in space, a cosmic fireball erupting outward into some pre-existing void. But the truth is far stranger. The Big Bang wasn't an explosion in space, it was the explosive expansion of space itself. Picture it like this: if you have dots on an inflating balloon, they don't move across the surface, the space between them stretches. Similarly, galaxies aren't flying apart through space. The space between them is growing, carrying them along like driftwood on a rising tide. Another common myth is that the Big Bang happened at a single point you could point to in the sky. But here's the mind-bending reality: it happened everywhere at once. Back when the universe was incredibly small, it wasn't a tiny speck floating in some larger emptiness, it was all there was. The entire observable universe, every particle and photon we see today, was compressed into that unfathomably hot, dense state. There was no outside for it to expand into, just as there's no edge or center to the universe today. This leads to another misconception, that the universe must have a center. If everything is moving apart, surely there's a middle point where it all began. Yet the evidence tells a different story. No matter where you look in the cosmos, distant galaxies appear to be receding from us in all directions. But crucially, observers in those galaxies would see the exact same thing. Every vantage point looks like the center of expansion. That's because space itself is stretching uniformly, like dough rising in an oven. The raisins' galaxies aren't fleeing from one another. The dough space is expanding between them. Even popular visuals of the Big Bang often get it wrong. Those artistic depictions of a bright flash erupting from darkness, they're misleading. The early universe wasn't black or empty. It was a blindingly bright plasma so dense, light couldn't travel far before bouncing off particles. It only became transparent when it cooled enough for atoms to form, releasing the cosmic microwave background we detect today. The real Big Bang is less like a detonation and more like the universe waking up, space stretching, energy condensing into matter, and temperatures dropping just enough for structure to emerge. It's a process without a center, without an edge, and without the fireworks we might expect. And that's what makes it so fascinating. It's not just a moment in history. It's the ongoing transformation of reality itself. The fate of the universe hinges on a silent tug of war, one we can't see but whose outcome will dictate everything. On one side stands dark energy, the mysterious force accelerating cosmic expansion. On the other, gravity's relentless pull, struggling to hold galaxies together. How this battle plays out will determine whether our cosmos drifts into icy solitude or is violently shredded apart. First, picture the Big Freeze, also called heat death. In this scenario, dark energy continues pushing galaxies apart at an ever-increasing rate, but space itself remains intact. Over trillions of years, stars burn out, black holes evaporate, and matter itself decays into a thin, lukewarm haze of particles. Galaxies beyond our local group vanish over the cosmic horizon, their light stretched beyond detectability. The universe doesn't end with a bang but a whisper, a vast dark graveyard where even atomic motion slows to a near halt. Thermodynamics wins, all energy gradients flatten, leaving no usable heat to power stars, life, or thought. Now contrast that with the far more dramatic Big Rip. Here, dark energy doesn't just accelerate expansion, it grows stronger over time, overpowering even the forces binding atoms together. First, galaxy clusters are torn apart. Then, individual galaxies, stars drift helplessly into the void. Months before the end, solar systems unravel. In the final minutes, planets are ripped from their stars. Atoms themselves disintegrate as the nuclear forces holding them together fail. Space-time, stretched beyond its limits, fractures at a quantum level. The universe doesn't fade, it's violently dismantled, piece by piece, down to the very fabric of reality. The key difference lies in dark energy's nature. If it behaves like Einstein's cosmological constant, unchanging over time, the Big Freeze wins. But if it's a phantom energy field that intensifies as space expands, the Big Rip becomes inevitable. Current observations lean toward the former, but the margin of error leaves room for terrifying possibilities. Some models even suggest dark energy could flip signs, reversing expansion into a catastrophic Big Crunch, a cosmic rewind to a singularity. What's haunting is how little we truly know. Dark energy could be vacuum energy, a dynamic field, or evidence of extra dimensions. Each possibility paints a different endgame. Future telescopes like Euclid and the Vera Rubin Observatory aim to measure dark energy's grip across cosmic history, searching for clues in the stretching of galaxy clusters or distortions in ancient light. Yet for all our theories, the universe keeps its ultimate secret close. Whether it's frozen silence or quantum chaos awaiting us, one truth remains. We're living in the brief, golden age where the cosmos is still alive enough to tell its story, and we're here just in time to listen. For all its brilliance, the Big Bang Theory isn't a cosmic full stop. It's more like a comma, leaving breathtaking questions in its wake. Take inflation, that staggering exponential expansion in the universe's first moments. We know how it smoothed and stretched the cosmos, but why it started or stopped remains a puzzle. Was it triggered by a quantum fluctuation in some exotic energy field? Did multiple inflating regions spawn a multiverse? The equations describe the mechanism beautifully, but the origin story is still missing its first page. Then there's dark energy, the enigmatic force pushing galaxies apart faster and faster. Accounting for nearly 70% of the universe's energy budget, it's the ultimate cosmic wildcard. Is it the cosmological constant Einstein imagined an intrinsic energy of empty space, or something dynamic like a field evolving over time? The challenge is stark. Quantum field theory predicts a vacuum energy strength 10 to the power of 120 times larger than what we observe. That's not just a gap, it's a yawning chasm between theory and reality, suggesting we're missing something fundamental. But perhaps the most profound rift lies at the singularity itself, the moment when general relativity and quantum mechanics collide in a storm of infinities. Relativity paints gravity as the curvature of space-time, while quantum mechanics rules the subatomic world with probabilities and uncertainty. At the Big Bang's inception, both theories should apply, yet they refuse to cooperate. Quantum gravity remains the holy grail, with string theory and loop quantum gravity as leading contenders. But until experiments perhaps detecting spacetime's granularity or higher dimensions give us traction, the universe's birth remains a paradox. Even the matter-antimatter asymmetry defies easy explanation. The Standard Model's CP violation, the slight preference for matter over antimatter, is too feeble to account for our existence. New physics like leptogenesis or undiscovered particles might hold the key. Meanwhile, the cosmic microwave background's anomalies, unexpected cold spots or odd alignments hint at phenomena beyond our current frameworks. The Big Bang isn't a finished story. It's a scaffold propping up our best understanding while leaving room for revolutions. Every unanswered question isn't a flaw, it's an invitation, a reminder that the universe is far stranger, far richer than we've yet dared to imagine. The next chapter of cosmology won't just fill gaps, it might rewrite the entire book. The moment science declared the universe had a birthday, pop culture couldn't resist turning cosmic origins into a punchline, a plot twist, even a sitcom theme song. Take the Big Bang Theory, where particle physics became prime-time entertainment. Those Sheldon Cooper's whiteboard scribbles were more accurate than his catchphrases. The show's writers walked a tightrope, blending real science with absurdity, like the time Leonard tried to explain cosmic inflation using a burrito analogy. For all its bazinga moments, the series did something revolutionary. It made cosmology dinner table conversation, even if viewers might confuse string theory with a malfunctioning guitar. Beyond sitcoms, the Big Bang became a metaphor for explosive creativity. Andy Warhol's 1987 Big Bang series smashed paint cans against canvases, literally splattering art into existence like a miniature universe. Musicians from Muse to Diana Ross riffed on it because what's more dramatic than a love song comparing heartbreak to the birth of spacetime? Even Doctor Who twisted the science with the Doctor quipping, "People assume time is a strict progression of cause to effect, but actually, it's more like a big ball of wibbly-wobbly, timey-wimey stuff." The line's nonsense, sure, but it captures the theory's cultural alchemy, turning mind-bending physics into something playful. Hollywood, of course, took liberties. Fantastic Four: Rise of the Silver Surfer turned the Big Bang into a cosmic reset button, while Men in Black reduced it to a marble in an alien's game. The irony, these wild misrepresentations kept the idea alive in public imagination. When Star Trek's Spock referenced the Big Bang hypothesis in 1967, most audiences had never heard the term. Fast forward 50 years and even toddlers know the universe went boom. Yet pop culture's greatest service might be its failures. Every time a show conflates the Big Bang with black holes or implies it happened in empty space, scientists collectively sigh, then seize the moment to clarify. Neil deGrasse Tyson's Cosmos rebutted myths by animating inflation like a rising loaf of raisin bread, while Vsauce's viral videos turned inaccuracies into teachable moments. The Big Bang's cultural journey proves a theory doesn't just live in textbooks, it thrives when it sparks curiosity, even through flawed interpretations. After all, if a Simpsons gag about the universe's first nacho makes someone Google cosmic microwave background radiation, that's a win for science. What's revealing is how the theory's metaphors shape our collective psyche. We call groundbreaking ideas Big Bangs, frame personal reinventions as cosmic reboots. The term has transcended astrophysics, becoming shorthand for any explosive beginning, proof that science, when wrapped in storytelling, doesn't just educate. It inspires. Whether it's a comic book hero's origin story or a pop star's lyric, the Big Bang endures not because it's perfectly understood, but because it reminds us every epoch has to start somewhere. From a singularity smaller than an atom to the vast cosmic web we see today, the universe's journey is nothing short of miraculous. Think about it. every galaxy, every star, every planet, including our own, traces its lineage back to that single, searing moment when space and time burst into existence. Over 13.8 billion years, the universe stretched, cooled, and transformed itself from a soup of pure energy into the rich, structured cosmos we call home. Gravity sculpted gas into stars, stars forged the elements of life in their cores, and generations of stellar explosions scattered those ingredients across the galaxy, setting the stage for planets and eventually for us. What's humbling is realizing how finely tuned this process had to be. If the initial density fluctuations from inflation had been slightly stronger, matter might have collapsed into black holes instead of galaxies. If dark energy had kicked in earlier, the cosmos could have ripped apart before life had a chance to emerge. Even the tiniest tweak to the fundamental constants, the strength of gravity, the mass of an electron, could have left the universe barren. Yet here we are, on a tiny rock orbiting an unremarkable star, able to trace our origins back to the very first moments of existence. This story isn't just about distant galaxies or abstract physics. It's your story, written in stardust. The iron in your blood came from a supernova's violent death. The calcium in your bones was forged in the heart of a dying star. Even the carbon that forms the backbone of your DNA was once scattered across interstellar space, waiting for gravity to pull it into a planet where life could take root. When you look up at the night sky, you're not just observing the universe, you're seeing where you came from. So let's end not with a conclusion, but with an invitation. The next time you step outside on a clear night, take a moment to really look. Those pinpricks of light aren't just decorations, they're part of the same epic that brought you into being. The atoms in your body, the thoughts in your mind, even the curiosity that led you to watch this video, they all began with a single, unimaginable spark. The universe didn't just create stars and galaxies, it created you, and if that doesn't leave you in awe, nothing will. Tell us in the comments what part of this cosmic journey resonates with you the most: the violent beauty of supernova, the eerie perfection of the cosmic microwave background, or maybe the simple, staggering fact that you're made of atoms older than the Earth itself. Let's keep wondering together, because the universe's story is still being written, and in a way, so is yours.